Okay, let's unpack this. When you're building, well, pretty much any software system today, you hit this really crucial choice, right?
Absolutely. How the different parts talk to each other.
Exactly. Through APIs. And it feels like maybe it's an overlooked detail sometimes, but the language, the protocol you pick, it can totally make or break things.
Oh, definitely. Choose wrong, and you're suddenly dealing with, sluggish performance, systems that can't scale, or maybe features you just can't implement, like getting instant updates.
It's like picking the wrong tool for the job, isn't it? You wouldn't use a hammer to saw wood.
Yeah, yeah. Or maybe like choosing that dirt path you mentioned earlier. Fine for a stroll, terrible for high-speed freight. The protocol sets the rules of the road for your data.
Right. And these sources we looked at, they really drive home that you need to understand the options to pick the right road. So that's our goal here, isn't it? To really get into the most common API protocols.
Yeah, figure out what they're good for, what their limits are, and importantly, help you think about how to choose based on your needs, speed, reliability, real-time stuff.
How the systems actually need to interact. Okay, so we're drawing on sources that cover everything from like the bedrock of the web up to real-time and high-performance links.
Exactly, from the basics to the more specialized tools. Should we maybe start with where these protocols even live in the grand scheme of things?
Good idea. They're not just floating in ether, right? There's a structure.
Right. They operate at what's called the application layer. Think of it as the top floor of the networking building. They rely on the floors below, the transport layers like TCP or UDP, to actually get data packets delivered reliably or quickly.
So TCP/UDP handle the delivery.
And the API protocols define the actual conversation between applications. Things like, what format do messages use? Is it question answer? Who talks first? How do we manage the connection? What do we do if something breaks?
They're the grammar and vocabulary for the apps themselves.
Okay, got it. So for anyone building web-connected things, where does that conversation usually kick off? Almost always with HTTP, Hypertext Transfer Protocol. It's the foundation of the web, and most web APIs build right on top of it.
The workhorse, yeah. What's its core interaction style?
Fundamentally, it's client-server, request-response. Your browser or your app that's the client sends a request.
Hey, I need this.
Exactly. And the server processes it and sends a response back. Okay, here it is. Or, nope, can't do that. But the key is the client always initiates. Each exchange is a distinct request, then a response.
One asks, the other answers. A turn-based conversation. Okay, let's quickly break down what's in that request because it seems like the blueprint for a lot of this.
Sure. The sources point out the main parts. You've got the method, that's the verb, like get to fetch data, posties to create new stuff, put to or patch to update, delete to remove.
The action you want to take.
Then the resource URL, what you want to act on, like API users 123. You've got the HTTP version, the host server name, and importantly, often authentication details.
Like a bearer token or basic auth to prove who you are.
Precisely. It's a structured way to ask.
Makes sense. And the server's reply, it's structured too, right?
Yep, mirrors it. You get the protocol version, headers with extra info, like content type, which is often application JSON for APIs these days.
But could be other things.
Right. And crucially, you get that status code.
Ah, the numbers. 200-something means it worked.
Generally, yeah. 200s are successic. 200 OK is the classic. 300s mean redirection. 400s mean the client messed up, like a 404 not found or 400 bad request.
My fault.
And 500s mean the server had a problem, like 500 internal server error. Understanding those is like API debugging 101.
Tells you where to start looking. Okay, so HTTP is that standard back and forth, but in today's world, there's something you absolutely need with it, right?
Security, no question. And that brings us to HTTPS.
Which isn't really a different protocol in terms of how it works.
Exactly. It's just HTTP, but the entire conversation is wrapped in an encrypted layer using TLSSL, secure HTTP.
And why is that basically mandatory now?
Because plain HTTP is like shouting across a crowded room. Anyone listening can hear everything.
Or sending that postcard, yeah.
Right. HTTPS encrypts it. So even if someone intercepts the traffic, they can't read the actual data. It ensures privacy, checks that the data wasn't tampered with, and helps authenticate the server. Plus, search engines like it.
So better security, data integrity, even SEO benefits. The sources call it the golden standard. Using plain HTTP seems risky.
Extremely risky for anything even remotely sensitive. Honestly, you just shouldn't do it. HTTPS is the baseline.
Okay, baseline established. Secure request response with HTTPS. But what about that limitation? The client always has to ask first. What if you need updates instantly, like, say, in a chat app?
Ah, yeah. That's the classic problem HTTP wasn't really designed for. That request response model means if the client wants to know if something new happened on the server, it has to ask again and again.
That sounds like polling, just constantly asking, anything new? How about now?
That's exactly what it is. And the chat example is perfect. Imagine your chat client asking the server every second, new messages, new messages. Most of the time the answer is nope.
Feels incredibly wasteful. Lots of requests, lots of network traffic, extra load on the server, and there's still a delay until the next poll, right?
Precisely. Wasted resources and built-in latency. That's where WebSockets come into play. They were designed specifically for this.
Okay, so how do they solve it?
After an initial HTTP handshake to upgrade the connection, a WebSocket creates a single, long-lived, bidirectional communication channel.
Bidirectional, that's the magic word.
That's the key difference, yeah. Once that tunnel is open, both the client and the server can send messages whenever they want, independently. The server doesn't wait for the client to ask anymore.
So a new chat message arrives at the server.
The server can immediately just push it down the WebSocket connection to the client, instantly.
Ah, okay. No polling needed after setup. And the client can still send messages up that same connection.
Yep, full two-way street, so you get real-time updates with minimal delay, and you drastically cut down on the unnecessary network chatter compared to polling. Much more efficient.
Got it. HTTPS for standard requests, WebSockets when you need that live push capability. What about other scenarios? Maybe less about instant updates and more about reliability, like making sure a task gets done eventually, even if systems are busy.
Right. That leads us to a different model entirely. Message queuing protocols. AMQP is a big one here. Advanced Message Queuing Protocol.
Okay, message queuing sounds different from a direct conversation.
It is. It's less about immediate request response and more about reliable, asynchronous delivery using a middleman, a message broker.
Okay, break down that model. Who talks to who?
So you have a producer, maybe your web service that takes new customer orders. Instead of trying to directly tell the inventory system, the shipping system, and the notification system about the order.
Which might be hard if one is down or slow.
Exactly. The producer just sends a message like, new order, ID 123, to a central message broker. Think of the broker like a post office with different mailboxes or queues.
And the other systems.
They're consumers. The inventory system subscribes to the order processing queue. When it's ready, it pulls the next message from that queue. The shipping system pulls from the ready-to-ship queue, maybe?
So the producer just drops the message off and trusts the broker?
Precisely. It decouples the systems. The producer doesn't care if the inventory system is busy or even offline temporarily. The message waits safely in the queue at the broker until the consumer picks it up.
So that guarantees the task processing the order eventually happens, even if there are hiccups or delays. Reliability.
That's the core benefit, yes. Reliability and managing workloads. Consumers pull messages when they have capacity, which helps smooth out peaks and troughs in activity. The sources mention different ways the broker can route messages too, but the main idea is that reliable, asynchronous handoff.
Okay, neat. Decoupled and reliable. Let's switch gears again. What if the absolute top priority is just raw speed, especially between services you control, maybe inside your own network?
Right, for that high-performance server-to-server chatter, especially in microservices, you often see gRPC come up. It's a framework from Google for remote procedure calls.
RPC. And what gives it the speed boost?
A couple of things. Firstly, it uses HTTP2 for transport.
The newer version of HTTP.
Yeah. And HTTP2 has built-in advantages like being able to run multiple requests over a single connection, compressing headers, stuff that makes it inherently faster than HTTP1 or beyond for many use cases.
Okay, so a faster foundation. Anything else?
It also typically uses protocol buffers, protobufs, for encoding the data. These are a binary format, usually much smaller and faster to parse than text formats like JSON or XML.
So faster transport, more efficient data format. Sounds good. Why is it mostly used server to server then, not typically from a web browser?
Well, while browsers do support HTTP2, fully supporting all the specific features gRPC relies on and making it easy to call from JavaScript is, let's say, less straightforward than standard HTTPS APIs. There are solutions like gRPC Web, but it adds complexity.
So simpler and more common between back-end services where you control both ends.
Exactly. In a microservices setup, where service A needs to call service B very quickly and efficiently, gRPC is a really strong contender. Plus, it has good support for streaming data built in, thanks again to HTTP2.
Okay, wow. So we've got HTTPS for the standard web stuff, WebSockets for real-time push, AMQP for reliable queues, and gRPC for speedy backend calls. That's quite the toolkit. How do you actually choose when you're faced with a new feature or system?
Yeah, that's the crux of it, isn't it? And the sources all kind of agree. It's about trade-offs. You have to look at your specific requirements. First, big question. What's the interaction pattern?
Like, do I need request response or real-time push or fire and forget queuing?
Exactly. That narrows it down a lot.
Yeah.
Then, performance. How fast does this really need to be? Is latency critical, especially between servers?
Okay, interaction pattern, performance needs. What else?
Client compatibility is huge. Can the things consuming the API actually speak this protocol easily? Browsers have limitations. Mobile apps might. Older systems definitely will.
Right, no point using gRPC if your main client is a simple web page that can't easily talk to it.
Precisely. Then you think about payload size. How much data are you sending? Security is always key. HTTPS is usually the answer there. And something that's easy to forget, developer experience.
How easy is it for the team to actually use this thing?
Yeah. Is the tooling good? Is it well documented? Is it easy to debug? Because a theoretically better protocol that slows your team down might not be the right practical choice.
That makes a lot of sense. You weigh all those factors. So general rules of thumb might be default to HTTPS for basic web APIs.
Use WebSockets if you need real time.
Look at AMQP for reliable background tasks or system integration.
And consider gRPC for high-speed internal service communication.
But it sounds like in any reasonably complex system, you might actually end up using several of these.
Oh, very likely. You might have a public API using HTTPS, internal services using gRPC, and maybe a WebSocket connection for live notifications, all within the same application. Pick the right tool for each specific communication job.
Okay, so we've covered the main protocols, HTTP, HTTPS, WebSockets, AMQP, gRPC, and the thinking process for choosing between them. Understanding these really gives you the foundation to build APIs that aren't just functional, but actually fit the specific needs of the system and the users.
It definitely moves you beyond a one-size-fits-all approach to API design.
And thinking about all this, drawing from the sources, maybe the really tough part isn't just knowing what HTTP or WebSockets are. Maybe the true challenge lies in that balancing act you mentioned. Making those trade-offs consciously, considering all those factors, performance, compatibility, developer ease, security, all at once for your specific project context. It's less about just knowing the protocols.
And more about the art and science of applying them effectively, yeah. It's architecture, it's about understanding the compromises. There's rarely one single perfect answer. The skill is really in diagnosing the specific communication need and picking the best fit or combination for that part of the system, even if it means using multiple protocols overall. It's about optimizing the whole, not just finding a favorite tool.